Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. So thank you for being here today. So my name is Dr. Su. You can call me Dr. Su. So I will continue structural analysis ECS 556. So this is topic number 3. Topic number 3 is actually called as stiffness method. Okay, for the stiffness method, I will actually refers to number one, the class note. Okay, the class note prepared by Dr. Teven, and most important is the textbook, the main textbook. Okay, the main textbook. Okay, this is the textbook. So the main textbook in this course is structural analysis by Hibler. Okay, by R.C. Hibler. And in the textbook, you can actually refer to this topic under three topics. Okay, 3 topics in the textbook. It is topic number 14. Topic number 14 is for thrust analysis. Topic number 15 is beam analysis, and topic number 16 is frame analysis. Okay, so I will mix my lecture today by highlighted what is important in the slide as well as in the textbook. Okay. So if you have any question, feel free to ask in the Q&A box, or you can also ask me any question in Teams conversation. In Teams conversation, okay, in Teams conversation, you can ask me directly, and I will answer you. Okay, within this session or after this session. Okay. So thrust analysis, stiffness method. Okay, we start with stiffness method. I refer to the notes first. Okay, so in this note, so I want to introduce you what is actually stiffness method. What is stiffness method? Okay, let's see what is the learning outcome first. The learning outcome, okay, for stiffness method. So stiffness method is actually another method that we can use to analyze structures. And the best about the stiffness method is we can use this method to analyze both determinate and indeterminate structure. Both determinate and indeterminate structure. Okay. So the learning outcome, number 1, by completing this chapter, you should be able to identify the constraint and unconstrained degree of freedom. Okay, identify constraint. Okay, the keyword is constraint and unconstrained degree of freedom. Degree of freedom for truss, beam, frame. Okay, and a bit about composite structure. And composite structure, okay, is a combination of bar element, EA element, as well as EI element in one structure. Okay, so truss, beam, and frame. So if we follow the textbook, okay, textbook starts with truss, followed by beam, followed by frame. Okay, and actually in stiffness method, compared to all okay, these 3 types, compared to these 3 types. Okay, wait. Okay, so in stiffness matrix method, we call this as stiffness matrix method. Matrix, the word matrix, matrix, because we will analyze, we will solve displacement, we will solve reaction, we will solve internal forces. Okay, using matrix. Okay, using matrix. Basically, it is matrix multiplication. Okay, it is matrix multiplication. Okay, so compare all these 4 types. Okay, listed in the learning outcome. Trust is the most simplest. Okay, the most simplest is for trust analysis. Then beam, then only frame. Okay, and then number 2, able to formulate member stiffness matrix. Okay, there is a word matrix. Displacement matrix. Displacement also we write in matrix. Force transformation matrix also we write in matrix. Okay, for truss, beam, frame, and composite structure. Okay, we focus on these three types. Okay, truss, beam, frame. Okay, and the last learning outcome is, okay, the most important is you have to be able to establish. Okay, we have establish what we call as local and global system. Okay, it is based on coordinate system XY coordinate system. So it has local system, it has global system in solving deformation, which is displacement, as well as forces. Okay, and actually in the textbook, so all examples, solution example is actually based on the global coordinate system. Okay, so before we move to the first part of the stiffness matrix method, as I mentioned, the first part is the truss. Okay, the first part is the truss. Okay, let me introduce you the difference between a stiffness method and flexibility method. Stiffness method and flexibility method. Okay, because stiffness method is a method to analyze indeterminate structure whenever equilibrium equation is not enough to determine the reaction. Okay, that is why we use flexibility method. And flexibility method has limitation. Flexibility method has limitation because we can only analyze structure up to 3 redundant only, when we want to solve for the reaction. Means total unknown reaction in the in the structure. When we analyze using flexibility method, total about 6 because 6 minus 3 will be solved. 3 will be chosen as redundant. Remaining 3 will be can be determined using equilibrium equation. So maximum redundant that we can solve using flexibility method, okay, is limited to 3. Because only 3 we can analyze using 3 simultaneous equation. Okay, 3 simultaneous equation. Okay, that is the limitation about flexibility method. Okay, however, using stiffness method, we can get more than 3, more than many reaction. We can get. Okay, we can get the reaction. We can calculate reaction for more than 3, for more than 4, more than 5, more than 6 as well. Okay. 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 What else? Okay. In flexibility method, we will get okay, in flexibility method, we will get reaction value, redundant. Redundant is reaction. Redundant is forces. Redundant can be reaction. Redundant can be member force. That is flexibility method. So that is why another name of flexibility method is force method. Okay, another name of flexibility method is force method. Force method. Why? Because the redundant is force. The redundant is reaction at the support, in beam, in frame, and the member forces can also be redundant, also forces, internal forces. Okay, that is why the other name of flexibility method is force method. Means that we get we get force, we get reaction first. We get reaction from flexibility. Okay, we get reaction. We get forces. Including reaction. Okay, reaction, and sometimes, and for, of course, in truss we can get member force. member force. Member force. Okay, force method. That is flexibility method. This is the output of flexibility method. However, using stiffness method, okay, the other name of stiffness method is displacement. Displacement method. The other name is displacement method, and the output, the first output that we can get from stiffness method, is displacement. And displacement for calculating displacement, unknown displacement, here will limit up to 3 unknown displacement, so that we can solve the unknown displacement. Okay, if in flexibility method we limit redundant up to 3, so that we can calculate the redundant using simultaneous equation. And since in stiffness method displacement is the first output, again we should limit the unknown displacement up to 3, so that we can analyze displacement using manual calculation. It is again simultaneous equation, even though it is written in matrix. Okay. And another advantage of using stiffness method is, okay, after we calculate displacement using what we call as force displacement equation, we calculate displacement using what we call as force displacement equation. Okay, it is force displacement equation. Okay, force displacement equation, it is also called as stiffness equation. Okay, stiffness equation. Force displacement equation is stiffness equation. Okay, it is just like flexibility method, where compatibility equation is actually flexibility equation. Okay, in stiffness method, we will have what we call as force displacement equation. And it is also called as stiffness equation. Okay, the first output in stiffness method, we will calculate displacement. Okay, we will calculate displacement whenever we solve force displacement equation. And after that, the displacement will be we can substitute the displacement back into the force displacement equation, and then we can calculate reaction. Forces. Okay, forces. Okay, however, under force method, under flexibility method, we cannot get displacement directly. Okay, under this, okay, we cannot get displacement directly. Okay, we cannot get displacement directly. Okay, we cannot get displacement directly. After we get forces, that's it. Then whenever we want to calculate displacement, we have to apply a unit load method 1 by 1 point in order to calculate displacement. But the advantage of using stiffness method, we use force displacement equation. To calculate number 1, displacement, number 2, reaction or forces. Okay, by using stiffness method. We can get these two output. Okay, under one method. Okay, that's the advantage of stiffness method. Okay, another advantage of stiffness method is we can get analyze both determinate. Okay, force method or flexibility method, we used to analyze indeterminate structure. Whenever three equilibrium equation is not enough to calculate reaction. That is why that is why flexibility method takes place. Okay, but using stiffness method, another advantage of using stiffness method is we can use stiffness method to analyze both. To analyze both determinate structure and indeterminate structure. Okay, so these are some of the advantages of using stiffness method compared to flexibility method. And of course, by using stiffness method, and stiffness method is actually okay, the theory behind structural engineering software. The theory, okay, the software, all the civil engineering software or structural engineering software is built, okay, based on stiffness method. So it will be easier, okay, for us to understand about stiffness method before we model the structure using structural engineering software. Okay, can be programmed in the software. So the step that we normally use whenever we want to model the software, model the building, for example, the structure in the software. The procedure will be the same as what we will analyze, okay, under stiffness method. Okay, if you have question, you can write in the Q&A box, okay, and I will try to answer your question. Okay, so what is stiffness? Okay, what is stiffness? Okay, actually, about deflection of bar element, because bar element okay, this bar element is actually element in structure. Is called as bar. Where under bar element it has AE. This is A. Yeah, it has AE. AE is actually axial rigidity. So under bar element, of course, we should deal with AE. Okay, so. And I just want to highlight some important things before we move straight away to truss, because bar element is actually element in truss is called as bar. Element in truss is called as some element in truss is also called as strut. Okay, but normally we use bar because bar has axial rigidity. Bar has axial rigidity, same element as in truss member. Okay, so okay, deflection of bar element. So we just focus on the keyword in bar element. So the keyword is, okay, remember this is the equation. Okay, F is equal to KD. Okay, in the textbook we use Q is equal to KD. Okay, Q is equal to KD. Q is forces, K is stiffness matrix, D is displacement. And remember, since stiffness method will be written all in matrix, so F in stiffness method is called as nodal forces. K is structure stiffness matrix. K is structure stiffness matrix, and D is nodal displacement. Okay, actually I don't want to explain in detail about bar element because I don't want to threaten you, because actually stiffness method compared to all four topics, Okay, 4 topics kan. You have learned flexibility. After this, you will learn moment distribution method. You have learned also many type of structure in under determinate structure, and actually structure stiffness. Stiffness method is the easiest. Okay, stiffness method is the easiest. So I don't want to threaten you about all the concept written in this bar element. Okay, so just focus on the keyword, the key point, the force displacement equation. It is Q is equal to KD. It is Q is equal to KD. So what is Q, what is K, what is D? Okay, as I written here. Okay, we will deal with coordinate system. That is why there is a word vector here, coordinate system. Okay, another important things that you need to understand under stiffness method is coordinate system. Coordinate system. Why we have to understand coordinate system? Because as I mentioned just now, stiffness method is the theory behind software. The theory behind software. So whenever we want to build model using software, of course we have to have the coordinate. So the coordinate, we have to set where is the origin, where is 0, 0. Okay, so coordinate system. So we have to understand what is coordinate system in stiffness matrix method. Coordinate system. So, okay. So bar element only have 2 degree of freedom. Okay, we will move straight away after this to thrust analysis. We follow the main reference, the textbook. Okay, advantages of stiffness method as I mentioned just now. Okay, as I mentioned just now, same like what I have just mentioned. Okay, analyze statically, analyze both statically determinate and indeterminate structure. Okay, the method yield displacement first and then forces. Number 1 is displacement, number 2 is forces. Number 1 is displacement. The first output when we analyze using stiffness method is displacement, then only forces, and then it is easier to formulate, okay, matrices for the computer operation. Okay, so this relate with the theory behind software is actually come from stiffness method. Okay, so the fundamental of stiffness method. Okay, fundamental. Okay, try to focus on the keyword. Okay, don't need to actually understand word by word. Just focus on the keyword. The keyword is divide, subdividing. The keyword is subdividing. Number 1, structure into element. Okay, structure into element. Ni nombor 2. Number 2. Okay, subdividing structure into element. So you need to understand that. When we want to analyze structure, truss, beam, and frame. Okay, truss, beam, frame. Okay, the major structure. Okay, truss, beam, frame. Okay, what we need to understand is under stiffness method, what we need to do is we have to divide structure into element. We have to divide structure into element. That is keyword. Okay, we have to divide structure. Okay, it is structure. What we get in the question? Either it is truss, or it is beam, or it is frame. Okay, all this is structure, complete structure. Whether it is determinate or indeterminate, so it is structure. So when we want to analyze using stiffness method, what we need to do is we have to divide into pieces, divide into element. For example, truss like this. Okay, this truss. Okay, loading here. Okay, this truss, 2 element, 2 members. Okay, 2 element or 2 members. This is structure. What we need to do, we have to divide into element. we have to divide into element. So we will start analysis by analyzing the element stiffness matrices. Element stiffness matrices. So we divide into elements. So this is structure. This is structure. This is element. Okay, element. We divide. So this has two elements. Element number 1, element number 2. We have to analyze element 1 and element 2 separately. We have to analyze element number 1 and element number 2 separately. Analyze what? We will analyze what we call as element stiffness matrices. That is the name. That is the term. Element stiffness matrices. And it is K1, okay, and K2. K1 and K2. Because this truss has two elements. This truss has two elements, element 1 and element 2. So we have to produce, we have to establish element stiffness matrices, K1 and K2. Okay, there is a formula given. Okay, K1, we have to produce like this, and K2. And for truss, we will produce, it is 4 by 4 matrix. It is 4 by 4 matrix for one element. So size of this matrix will be depend on the degree of freedom. Will be depend on degree of freedom. Will be depend on the degree of freedom, the size. Okay, the size. Okay, next. The force displacement properties. Force displacement properties of each element. Okay, try to relate to software, so structural software, where the first step is after you start with 1 point, you build the element. You combine two points, 2 nodes become one element, and then you combine element to become structure. Okay, in the software. And after that, we will apply what we call as force displacement properties. Force displacement properties. Okay, in the software, force displacement properties refers to support. Okay, refers to support. So in the software, we have to label support. We have to label, and we have to put support, whether it is fixed support, whether it is roller support, whether it is pin support. Okay, and then we have to apply the what we call as cross section area, geometric. Okay, it is properties. Okay, cross section area, we have to apply material properties. Okay, we have to apply material properties. Okay, material properties refers to E. Okay, the modulus of elasticity. Okay, force displacement properties including boundary condition. Okay, force displacement properties. Okay, force displacement properties. Okay, force displacement properties including, okay, this is actually Q is equal to KD. And in order to produce this, if we try to relate with the software, after we build the model, we build the point, the element and the structure, we have to apply boundary condition. We have to apply what we call as boundary condition. This is all the properties. Boundary condition. What is boundary condition? Boundary condition is support. Boundary condition is support. Boundary condition. And support is constraint. Constraint degree of freedom. Okay. In the software, we use the term boundary condition. Okay. And boundary condition is actually support system. Either it is pin support, it is roller support, it is pin support, boundary condition. Okay, and in stiffness method, okay, support is actually constraint degree of freedom. Constraint degree of freedom. So the most important term in this topic that you need to understand is degree of freedom, because degree of freedom, okay, we should be able to differentiate between unconstrained and constrained degree of freedom system. And under support, due to support, okay, there is a constraint degree of freedom. Okay, boundary condition. Another properties that we should understand, okay, under force displacement properties is called as section properties. Section properties. Okay, in the software, if you use software previously, maybe under diploma in part 6, you use esteem, right, to model the building. Okay, to model the building, and you actually have used all this term previously. Okay, so section properties, okay, under force displacement properties as well. What is section properties? Section properties is cross-section area. Okay, relate with I, moment of inertia, or A, area. Area for truss, I for beam. Combination of I and A for frame. Okay, A for truss, I for beam. And I plus A in frame, as well as composite structure. Okay, section properties. Section properties. Because from cross section we can analyze also the moment of inertia. Okay, so we have to define the section properties in our model that we built in the software. Okay, we have to define. Okay, that is why under formula of displacement, we have to have I, moment of inertia, for example, or we have to have area if it is thrust. Okay, in order for us to calculate displacement, because displacement will relate with all this. Okay, so next properties that we need to understand, and we include these properties every time we analyze structure, every time we analyze displacement of the structure. Number 3 is called as section properties, material properties. Material properties. Material properties. What is material properties? It is modulus Young. It is modulus of elasticity. Okay, modulus of elasticity. So again, whenever we build the model, okay, after we put support, after we define the section properties, we have to choose the material used, whether it is reinforced concrete, whether it is steel, what should be the value, what is the value of E for steel. Okay, for aluminium, for example, we should define the material properties. And material properties, okay, actually will influence the displacement, the forces that we get. Okay, material properties, E. Okay, that is why under formula of displacement, you have learned previously as well, under flexibility method or under unit load method, whenever we analyze displacement, we include all this. We have all this in the formula. We have E inside the formula. We have I inside in the formula, because all this, okay, is actually under force displacement properties. Force displacement properties. Okay. Okay, next. Okay, next. The unknown displacement. Okay, the four displacement properties are then determined, and this relationship are then formed as the structure stiffness metric. Okay, and between Q and D, between Q and D, there is a coefficient between Q and D. Q is forces, D is displacement. Q is forces, D is displacement, and between these two there is a coefficient. Okay, so in stiffness method, the coefficient, okay, to relate Q and D is K, and K is stiffness matrix, the structure stiffness matrix. What is K? K is structure stiffness matrix. K is capital K, capital K. It is capital K. It is capital K. K is structure stiffness matrix. And how to get this? How to get this? It is combination of element stiffness matrices. Just now we get K1 and K2. K1 for element 1, K2 for element 2. So we have to combine it back to get back the structure. Okay, it is called as structure stiffness matrix. Okay, plus K, and N is number of element in the structure. Okay, K, this is capital K. Capital K is for structure stiffness matrix. Small k is for element stiffness matrices. Element stiffness matrices. If you have question, you can write your question under Q&A. Okay, in the live event chat box, or you can also ask me in the Teams conversation. Okay, Teams conversation, you just reply the link. Okay, at the link given, so you just can ask me any question there. Okay, structure stiffness matrix. Okay, capital K. We use capital K here. Capital K here. Okay, the unknown displacement. The unknown displacement. Once we have got K. Okay, D, Q. Okay, this is force displacement equation. So we have to establish K. We have to establish the right stiffness matrix, structure stiffness matrix. And then we have to write the Q, nodal forces in matrix. We have to write nodal displacement as well in matrix. And by applying boundary condition, by applying unconstrained and constrained degree of freedom into the force displacement equation, we will calculate the unknown displacement. We will calculate the unknown displacement as the first output, and after that we will calculate the forces as the second output. Okay, forces as the second output. Displacement, after that forces. Okay. So this is just the process. I don't want to go in detail about this. Okay, procedure doesn't matter. So the same procedure. So we just need to remember how to remember the procedure. How to remember the procedure. Okay, recall back to the model that we built in the software. Recall back to the model that we built in the software. What we need whenever we build the model in the software. Number one, we have to have coordinate system. We have to have coordinate system, and then we have to have the to set origin. We have to label each joint, each coordinate. We have to label coordinate for each joint. Okay, we have to label coordinate for each joint. But before that, we have to be able to differentiate between unconstrained and constrained system. So we just need to follow that. And then from element stiffness matrices, K1, K2, we produce structure stiffness matrix, capital K. And after that, we apply force displacement equation. And after that, we solve displacement, unknown displacement. And once we have determined the unknown displacement, we continue to calculate reaction or forces. Okay, that's the step. Okay, so I want to move to the textbook. Okay, wait. Okay. Actually, I have this in the OneNote as well, but I can open. So, okay, tak apa. We use this in I open this textbook here. Okay. So as I said just now, this is topic number 14. This is topic number 14 in the Hibler textbook. Okay. Chapter number 15 is beam. Okay. The easiest is this, the truss. Okay. The easiest is this, the truss. And then beam, and then frame. Okay, so okay, let's try to understand about stiffness matrix analysis. Okay, for truss. Okay, in this chapter we will explain the basic fundamental of using stiffness method for analyzing structures. It will be shown that this method, although okay, tedious to do by hand, okay, it quite suit for use on a computer. Okay, tedious to do by hand whenever we have more than 3 unknown displacement, because only 3 unknown displacement can be solved using manual calculation. Okay, and then okay, beam and frame will be discussed in the next chapters. Fundamental of stiffness method. Actually, the fundamental I have described earlier by using the slide note just now. Okay, so this one I leave it to you to read on your own. I will put this note in the OneNote, class notebook. So in Teams you have in Teams. Okay, wait, I open the Teams. Okay, this is the Teams. Okay, this is your team. Okay, this is your Teams. So under this team, there is one part here. That is class notebook. That is class notebook. And class notebook is OneNote. Class notebook is OneNote. And and actually every one of you, after I created this, okay, these teams, I have generated, okay, your OneNote class notebook. Your OneNote class notebook, so you can actually refer to what we discussed today. Okay, to what we discussed today, which is under your own OneNote. If you install your OneNote into your phone, okay, or into your tablet, or you can also open OneNote in Teams. You can also open OneNote in the browser, okay, in any browser, okay. So you can actually refer back to, okay, the notes that I have explained just now, okay, under content library. Okay, it is under content library for you to maybe revise it back after the class session. Okay, you can okay, open under class note, open under, okay, under, where is it? Stiffness method. It is stiffness method. Chapter 1, flexibility. This is flexibility. This is flexibility. Oh, this is CS521. No. You have to open your team. Sorry. You have to open your teams. It is ECS556. Where is it? Okay, this one. Okay, this is ECS556. So ECS556. Okay. So it is under class notebook. Okay, it is under class notebook. So you can Okay, I encourage you to ask me anything about lecture, any question regarding stiffness method. Okay, you can ask me directly in this conversation box. Okay, directly in the conversation box. Okay, I put it here. Okay, so you can ask me if you want to ask me directly. Okay, in this Teams conversation. Okay, this is the class notebook, and it is actually OneNote. So if you download OneNote in your phone, you can actually access to whatever content that we discuss using your own. Okay, using your own apps. Okay, so this is class notebook. You can open directly using OneNote apps because I have generated it for you. So this is all okay, your name. This is all your name. So you have your own OneNote where you can actually submit you can actually put whatever exercises that you do. You put it under your own folder. Okay, you have your own only me have all list of student. Okay, so you can put any exercises that you want me to check. Okay, you can put directly under your own OneNote, and I can check for you. Okay, so this is your own. Okay, and I actually discussed about the stiffness method just now under content library. Under content library. Okay, under content library. Okay, not necessarily you open this in Teams. You can open this directly using your own OneNote. Using your own OneNote. So I just now use content library. So under content library, under class note. Okay, under class note. Okay, under topic 3. Under topic 3, this is what I explained to you just now. So you can revise it back by opening, okay, by opening this OneNote. Okay, by opening this OneNote. This is the one. Okay, this is the one. Okay. This is the one. So you can use it back for your reference. Okay, you can use this for your reference. Okay, so after this I will put the textbook as well. Actually, I have created this textbook by I don't put anything yet. I don't put anything. I just put under CS521, not this group. I will transfer the textbook as well, chapter number 14, 15, and 16 here. So that after this, whatever we discuss in class, whatever I annotate during class session, you can refer back after the session. Okay, so this is class note. Class note. Okay, I will use under class note. Okay, I want to add another. Okay, under this topic number 3. It is topic number 3. Under this topic number 3. Okay. Okay, this OneNote managed by me. This OneNote managed by me. So I created one for week. So this is week number 10, right? Week. So week number 10. It's for week number 10. Okay, so go back to this. Okay, later on I will put this note into the OneNote as well. Okay, so the fundamental, like what I have explained just now, it is the same. Because, so all notes, even though you download notes from other universities, because we can find this topic all around the world. Okay, so all notes, you can find the notes that is actually referring to the same textbook. Okay, So what I want to highlight is about this. Okay, this one in the textbook. Okay, member and node identification. Member and node identification. Okay, member and node identification. Member is element. Member is element. Conventionally, when we analyze trust, okay, determinate trust, for example, we label as ABC. Remember, ABC. And we call it as member AB. We call it as member BC in trust. But whenever we transform the trust into the software, we don't label it as A, B, and C, because labeling member or labeling nodes using A, B, and C has limitation. That is why in the software, when we build model, structure model in the software, we label node using numbering. We label element as well using numbering. Member is element. We label member using numbering as well. Because when we use software, we normally build with a model with 1,000 element, maybe 1,000 nodes. Okay, the huge structure. So we cannot use ABC in the software. And always remember, the stiffness method is the theory behind software. So whatever procedure that we use here, it is exactly the procedure that computer do. Whenever we ask the computer to calculate the reaction, calculate the displacement, that is the procedure. So in stiffness method, you have to get familiar to number the joint A, joint B, joint C. Conventionally, we transform to node 1, node 2, node 3. That is called as node. Okay, we call it as node. We call it as node. It is node. Okay, what is member? Member. Normally, we can call it as member. We can call it as element. Okay, in the software, we use as element. Element represent member. Okay, but element, we call it as element 1. We don't call as element AB. We don't call as element BC, because element we call by numbering. Element number 1, element number 2, element number 3, element number 60, element number 100, element number 99. That is actually member. Okay. So one of the first step when applying stiffness method is to identify element or members. Okay. When we use member, normally we use as member AB, member BC, member CD. Remember, in software, we use the term element, and we call element as element 1, element 2, element 3, and so on. Okay? Of the structure and their nodes. Okay, node is join. Node is join. We will specify each member by a number. Okay, by a number. Enclose within a square and use a number to enclose within a circle to identify the nodes. Okay, and then we have to be able to define, okay, the node as near and far node. Near and far node. We have to label whether one element consists of two nodes. So which is the near node, which is the far node. We have to be able to recognize it. Okay, we must identify that. This will be done by using the arrow. So how to define the member? How to define the near node, the far end node, the near end node, is by using the arrow. using the arrow. Okay, using the arrow. We have to put the arrow. We have to put the arrow in any direction that we like. Okay, we have to put the arrow in any direction that we like. And the arrow is important to identify near and far end nodes. Okay, near and far end. Near and far end. How to identify near? How to identify far? By looking at the arrow. By looking at the arrow. With the head of the arrow is far end. The head of the arrow is far end. Okay. Okay, head of the arrow is far end. It is like this. Okay, when we have one element, okay, I maybe draw under the one node. Okay, under the one node, okay, this is 556. This is 556. Okay, this is week 10, week 10. Okay. Here, number one, the most important thing is degree of freedom. Degree of freedom. Degree of freedom, we have to identify this under two conditions. Number one is called as unconstrained. Number two is called as constrained. Okay, unconstrained and constrained. Unconstrained and constrained. For example, if we have one truss like this. One truss like this is two pin jointed plain truss. Pin jointed plain truss, this is force. Okay, this is force. This is two element. How we know that this is two element? Because okay, these two element, okay, we two element, this has two element. Element, what is element? Element we get from two nodes. Means that to produce structure, we start with node, we start with point. Node. Okay. Okay, the first thing is it is nodes. It is node. It is node. There is point in the structure. Okay, node. This node, when we combine two nodes, it become one element. Okay, when we combine two nodes, it become one element. When we combine two nodes, it become one element. So this one, as I have shown to you previously, this is structure. So what we need to do is we have to divide the structure into element. Divide the structure into elements. So when we divide this, we divide into this. Okay, we divide into this. Okay, so how many elements? We have two elements. We have two elements. For example, this is element number 1. This is element number 2. Two element. And normally, element we label by number inside box. Element, that is label for element. Label for element. So one element consists of two nodes. To get one element, we must have two nodes. When we combine two nodes, we have one element. Okay, when we combine two nodes, we get one element. So element number 1. Okay, normally we don't label element node here with element nodes in the structure. Okay, how many nodes? How many join that we have in this truss? How many join? Normally we label as A, B, C, right? Normally we label as A, B, and C. Normally we label as A, B, and C. But as I mentioned in stiffness method, we have to change to number. So we label A as 1. We label B as 2. We label C as 3. So we have 3 nodes. We have 3 nodes. How many members? How many members? We have member number 1. We have member number 1. We have member number 2. we have member number 1, member number 2, or it is element number 1 and element number 2. Okay, start with note, start with identifying notes. Start with identifying note. What is note? It is join. Okay, it is join. So in this truss, there are 3 join representing by 3 notes. Note 1, note 2, note 3. And remember, we have to divide this truss into element. So how many element? We have 2 element. We have element number 1. Element number 1 combining note number 2 and note number 1. Element number 1 combining note number 2 and note number 1. And we have element number 2 combining note number 2 and note number 3. Okay, again, element number 1 combining note number 2 and note number 1. Okay, and element number 2 combining note number 2 and note number 3. Okay, so this one I have drawn separately, element 1 and element 2. So this will be note number 1, this will be note number 2. So this note number 2, again, this is note number 2, this is note number 3. Okay, so from this element, we should label the arrow. We should label the arrow. So what we need to do is we just need to label the arrow, which is parallel with member. Label like this. Okay, and we can put the arrow in any direction, doesn't matter. Okay, we can label the arrow. Okay. Okay, the first thing that we need to make sure, okay, exists in the free body diagram of the structure of the truss. Whenever we want to analyze this truss using stiffness method, number 1, we have to identifying nodes. Identifying nodes. That is number 1. So we have identify nodes. We have 3 nodes. Node number 1, node number 2, and node number 3. Okay, step number 2. Okay. Step number 2, we have to identify element. So step number 2 is identifying elements. Step number 2. Okay, step number 2. Number 3. Okay, number 3, we have to put arrow. Because we have to label near end and far end for each element. Okay, number 3, what should be put inside the free body diagram of the truss? Okay, it is an arrow. Okay, put the arrow. For each element, put arrow in each element, and it must be parallel like this, arrow. So why we need to put arrow? It is very important. If you don't put arrow, you cannot identify which node is near node, which node is far node. And the best thing is we can put arrow in any direction that we like. So I follow back the arrow that I have put in the main diagram. Okay, this is the arrow. So remember, the arrow is always going towards far end. The arrow is always going forward far end. Okay, so arrow to always going to the far end. Always going to the far end. So at the back of the arrow, it is near. Okay, this is how we identify near nodes, near end nodes, and far end nodes. We identify from the arrow. Okay, let's do the same for element number 2. Since the arrow is going towards node number 3, so node number 3 will become far end. So the other one will be the near end. And always remember, we can label, okay, we can put arrow in any direction that we like, doesn't matter. Okay, anyhow it will be, okay, it will influence the position of near and far end. Okay, always remember, arrow is always going to the far end. Arrow is always going to the far end. Okay. So next is coordinate. Next is coordinate. Okay, next is coordinate. Normally the question we have like this. Okay, the conventional way of question is like this. Okay, let's say this is ABC. For example, this is ABC. Conventionally like this is the question. So this is 3 meter, this is 4 meter. Okay, this is load 200, for example, kilonewton. It is like this. So having this, since stiffness method based on coordinate system, we should, okay, transform this into coordinate system. Means that every nodes we have to label by coordinate. Every nodes we have to label by coordinate. Okay, every nodes we have to label by coordinate. So, okay, what should we do? We should, number 1, choose one node as origin. Choose one node as origin. So, choose one node as origin means we have 3 nodes, 1, 2, and 3. 1, 2, and 3. And this is only the tips. Okay, this is only the tips. Whenever we want to choose origin. Okay, whenever we want to choose origin. It is, okay, it is like this. Choose one node as origin. Choose one node as origin. Choose one node as origin. And the node that we choose, okay, the node that we choose will be labeled as 0, 0. Will be labeled as 0, 0. Okay, will be labeled as 0, 0. And from this origin, we continue to label, okay, the remaining. Okay, from this, we will label node number 3 as 4, 0. And we continue to label node number 1 as 4, 3. 4, 3. Okay, by choosing origin. Choosing origin. One node as origin. Okay, why I choose 2 as origin? Can I choose 1 as origin? Can I choose 1 as origin? Or can I choose 3 as origin? Okay, the answer is yes. The answer is yes, but, okay, when I choose 1 as origin, one will be 0, 0. 1 will be 0, 0. So when 1 is 0, 0, I will have negative coordinate for 2 and 3. Okay? And if I choose 3 as origin, I will have node number 2 with negative coordinate. So that is why I choose 2 as origin. So when 2 is become origin, 2 is 0, 0. So when 2 is 0, 0, coordinate 1, coordinate for node number 1 will be positive, and coordinate for node number 3 will be positive as well. Okay, and however, this is only the tips to get all positive coordinate in the structure. Okay, so I have listed here number 4. Number 4 is coordinate. Put coordinate. Okay, and number 5, the most important part is to label degree of freedom. We have to label degree of freedom. Okay, label degree of freedom in this trust. We have to label degree of freedom in this trust according to unconstrained. Number 1. Number 2, constraint. Okay, this is the most important part. This is the most important part. Okay, so always remember this step. Okay, all these 5 steps, okay, must be putting in the diagram. It is called as the free body diagram. Free body diagram for structure when we want to analyze the structure using stiffness matrix method. Okay, I hope you clear about this. Because next I want to explain about the degree of freedom. Okay, about the degree of freedom. And degree of freedom, okay, the understanding about degree of freedom is very, very important, because actually analysis of truss, analysis of beam, analysis of frame, okay, as well as composite structure. Okay, the most important thing is the procedure is all same for all types of structure. So what's the difference? The difference is due to degree of freedom. The difference is due to degree of freedom. So what is actually degree of freedom? Okay, so we go to, okay, the most important part in stiffness method, that is understanding degree of freedom. Understanding degree of freedom. Understanding degree of freedom. Okay, there is an explanation in the textbook that you can read. Okay, there is an explanation about degree of freedom in the textbook that you can read. And it is actually, okay, it is actually the term degree of freedom. The term degree of freedom is actually refers to displacement component. Refers to displacement component. Degree of freedom. The term that used in the textbook. Okay, what is degree of freedom? Degree of freedom is displacement component. And displacement component relate also with forces. Okay, displacement also with forces. Okay, and displacement component that you have actually learned previously under previous topic. Maybe in diploma, you have also learned about the degree of freedom. Okay, that maybe you do not recognize it as degree of freedom. Okay, it is displacement component is the term component. Okay, relate with support. Okay, relate with support condition or boundary condition just now. Relate with support system. Okay, relate with support system like this. It is like this. In static analysis, okay, okay, it will reflect as well with the three equilibrium equation. Remember, when we want to analyze structure, we have to take moment. Okay, take total moment. Number one, take total horizontal force and total horizontal vertical force. Three direction. Okay, this three direction is also refers to displacement component. It is in X direction. It is in Y direction. It is in moment direction. Moment is Z direction. Okay, Z direction, rotational displacement. Okay, displacement component here refers to X component, Y component, and Z component. Okay, this is degree of freedom. Okay, this is the three component. We have component in X, we have component in Y, we have component in Z. Okay, we have component in Z. We have three component. We have three component. Component in X. So, and this component must be related with Q and D. Must be related with Q and D. This component means that we have to have Q under these three component. We have to have displacement under these three component. Okay, under these three component, Q and D. So this component is not only for displacement. It is also for forces. Relate with both Q and D. Okay, X, Y, and Z. X, Y, and Z is the component. So this X, Y, and Z must be relate with Q and D. So between this component, okay, I try to tabulate it so that you can understand more about this. Okay, this is component. This is component. Okay, Q is forces, D is displacement, and we have component X, component Y, and component Z. Component X, component Y, and component Z. Okay, so this one, okay, this one is stable. We have X, we have Y, we have Z. Okay, X, Y, Z is component. X, Y, Z is component. X, Y, Z is component. So if it is Q, if it is force relate with X component. Force relate with X component is horizontal force. Or if we relate with one point A for example, point A for example, if we try to relate with point A, 1 point, and 1 point, let's say this is A, or this is node number 1. Okay, this is node, node. Okay, so it relate with, if it is Q, for position or for node A, we always call it as AX. Okay, that is forces. Horizontal force at A. Horizontal force at A. We can also label as H for horizontal force, HA. Okay, we can also label as any if it is for A, for position A. If it is for B, it is BX. If it is for D, it is DX. Okay, so we can also label as H. Okay, so A means the position. Okay, the position. Okay, Y at position A, it is AY. Vertical force, vertical reaction at A. Vertical reaction at A, sometimes we label as VA, but normally we label as AY, AX. And forces, okay, in component of Z, okay, force in component of Z is moment at A. It is capital M, capital M. It is moment. Moment at A. Moment at A. Okay. So these are displacement. Forces. Q. Q is forces. Q is forces. There are 3 components. Component X, component Y, component Z. Component X, component Y, component Z. So in component X, okay, we normally call it as horizontal force or horizontal reaction. Horizontal force. Okay, if it is located at the support, it is horizontal reaction. Okay, if it is in Y component, it is a vertical force. Or if it is located at support, it is vertical reaction. And if it is representing moment, it is moment at position A or moment at position B. So that's represent component Z. That's represent component Z. Okay, that's about forces. Now we move to displacement. So displacement also has 3 components. In static analysis, we have 3 components, X, Y, and Z. So we have horizontal displacement. Okay, normally, conventionally, we label as delta. Delta in X. Horizontal displacement. Okay, and for Y component, we label also as delta in Y component. Delta in Y component, delta Y. Delta in Y component is delta Y. And Z is rotational displacement. It is theta. Okay, it is theta. Okay, theta represent Z component. Theta represents Z component. We call it as rotational displacement. Horizontal displacement, vertical displacement, rotational displacement. Horizontal displacement, vertical displacement, and rotational displacement. Rotational displacement we normally call as rotation. We normally call as slope. Okay, rotational displacement, slope is the same. Okay? This is the component about degree of freedom. About degree of freedom. And this we must relate with support. We must relate with support. So we have to understand the support condition. We have to understand support condition. And we need to understand also that the characteristic, okay, the characteristic of these two, Q and D, will be opposite. Okay, the characteristic will be opposite. Opposite means if one is known, one is unknown. Opposite. One is 0, one is non-zero. One is 0, one is non-zero. One is known, one is unknown. That's the meaning of opposite characteristic between Q and D. Okay, between Q and D. And we should read that characteristic from support. Okay, from support. Okay. Okay. So I will use okay, support. So there are three types of support. There are three types of support. Okay. So you have learned about support. Okay, when you learn structure. You have learned about support when you learn structure. We have fixed support. We have fixed support like this. Fixed support. And for fixed support, we have all these three components. All these three components represent reaction at the support. Represent reaction at the support. So what happened? What happened? Represent reaction at the support means represent if this is A, represent AY, AX, and moment at A. When it is fixed. When it is fixed. Okay, this is all due to fixed. We call it as unknown reaction. Unknown reaction. Unknown reaction. What happened? Okay, what happened? Unknown versus known. Unknown versus known. Unknown versus known versus known. Unknown versus known. Known value means known value. Okay, this is unknown. Unknown reaction means unknown Q. Unknown reaction means unknown Q. Unknown reaction means unknown Q because reaction is force. Reaction is force. Okay, unknown Q. So as I mentioned, between Q and D, the condition is always opposite condition. If it is Q as unknown versus known, known is belong to D, known displacement. It is known displacement. So what is the value if we call it as known displacement? Known displacement. Known displacement. Displacement at these three components. At fixed support, displacement at these three components equal 0. Displacement due to these three components due to fixed support equal 0. That is why when we draw, for example, deflection in cantilever beam. Okay, for example, this is how we understand the concept of degree of freedom. Okay, so degree of freedom ni we try to understand about all beam, frame, and truss as well. Okay. Non-displacement. Non-displacement here, why we call it as non-displacement? Okay, I try to draw this. I hope you understand. Okay, about this. Okay, cantilever beam. cantilever beam, the one that you have learned, okay, under determinate structure, maybe under diploma, under solid mechanic, determinate beam. This is cantilever beam. The cantilever beam, when we draw deflected shape of this beam, when we draw the deflected shape of this beam, we draw from here. That is because there is no vertical, there is no okay, horizontal first. Horizontal displacement at A equals 0. Vertical displacement at A equals 0. And there's no rotation as well. Theta at A equals 0. This means non-displacement. This means non-displacement. This is non-displacement. So what is the value? Displacement equal to 0. Displacement equal to 0. So non-displacement here means displacement equal to 0. Because of the support. At the support, there's no displacement. At support, no displacement. If it is fixed, it is fixed. There are 3 unknown reaction, 3 unknown reaction, 3 unknown reaction. Okay, means that there are 3 non-displacement. Okay, so we can also, beside call this as unknown reaction and non-displacement. Okay, we can categorize this as non-zero displacement versus zero displacement. So this occur in constraint system. This occur in constraint degree of freedom system, and this one, the boundary. Okay, the boundary. Okay, unconstrained system. Okay, non-zero versus zero, unknown versus known. Okay, that's for fixed end. Okay, what happened for pin? For pin. So okay, let's say I draw for you now simply supported beam. Okay, simply supported beam. Simply supported beam subjected to loading, UDL again. Okay, what is the shape for this deflection due to the loading? Okay, we normally draw like this. Okay, we draw like this, and okay, we have tangent here. We have tangent here, and the tangent is representing the slope. The tangent representing slope. Okay, so this is theta. So let's say this is A, this is B. So this is also theta, slope. By looking at this, we know that theta at A is not equal to 0. Theta at B is not equal to 0. Okay, so other than this, okay, we have reaction at fixed support, and reaction at fixed support is AY and AX, right? AY and AX. By understanding pin, it has 2 unknown reaction. Understanding pin support, there are 2 unknown reaction. 2 unknown reaction. 2 unknown reaction means if we look at the support, okay, look at the support in opposite condition, it represent delta in x equal to 0, delta in y equal to 0. That is why ax and ay, these two are called as reaction at A reactions. So this is unknown reaction. How many? 2 unknown reaction for pin support. 2 unknown reaction for pin support. 2 unknown reaction for pin support. Okay. So in conclusion, when we understand about the support system, it is I can conclude like this. We have fixed. Okay, we have fixed. We have pin. We have a roller. Okay, in terms of number of unknown reaction. Number of unknown reaction. Okay, unknown reaction. Okay, the label is Q. The label is Q. Okay, for fixed, we have 3 unknown reaction. For pin, we have 2 unknown reaction. For roller, we have 1 unknown reaction. And in opposite condition for D, for displacement, okay, for displacement, okay, for displacement, okay, it is 3. This will become, okay, okay, let's look at like this. Okay, unknown reaction, and unknown displacement. Unknown reaction and unknown displacement. Okay, if it is 3, means that displacement, okay, this is known displacement. Known displacement or equal to D is equal to 0. Okay, D is equal to 0, known displacement. This one is non-zero displacement. Non-zero displacement. 0 versus non-zero. Okay, unknown reaction. Okay, so if it is fixed and non-displacement, number of displacement equal to 0 is 3. Okay, number of displacement equal to 0 is 3. Okay, and if it is pin support, okay, if it is pin support, number of unknown reaction is 2. So number of displacement equal to 0 is 2. And if it is roller support, number of displacement equal to 0 is 1. So this is unknown displacement. Okay, unknown displacement. This is unknown displacement. Okay, this is unknown displacement. Okay, unknown displacement, this is unknown reaction. Unknown displacement versus unknown reaction. Unknown displacement versus unknown reaction. Non-zero versus 0 displacement. Okay, like this. Okay, so the one that is called as degree of freedom is this. Degree of freedom. Referring to this. Okay. So if it is pin support, if it is truss structure, because in truss there's no fixed truss, truss only has pin, truss only has roller, so means that we don't have moment in truss, So we have to remove and count only 2 degree of freedom in truss. So in truss, okay, in truss we only count 2 degree of freedom in X and in Y direction, okay, because there is no moment. Okay, there is no moment. Yang ni concept for all. This is concept for all. However, when we analyze structure by structure, okay, when we analyze truss, we only count displacement or degree of freedom equal to 2. Equal to 2 because we don't calculate moment in truss. Truss has no moment, so we don't need to have Z component in truss. Z component in truss. So we only have 2 degree of freedom in truss. Okay, then when we move to beam, how many degree of freedom? How many degree of freedom? Okay, in beam they are, okay, we count as 2 as well. We count as 2 as well, beam, because in beam horizontal force and horizontal displacement equal 0. The displacement in beam can be neglected. The displacement in beam can be neglected. Okay, sorry. Actually, I am under quarantine right now, so I'm in home. Okay. Okay, about degree of freedom. Okay, go back to degree of freedom. Okay. Okay, we want to summarize about degree of freedom. That is very, very important. Okay, what I can conclude is in truss, we have 2 degree of freedom. We have 2 degree of freedom in X and in Y direction because we have no moment. We have no rotation in truss. That is why we only count 2 degree of freedom in truss as 2. And this will be the sign convention for truss in the direction that I draw here. X in the right direction, Y in upward direction. This will be the sign convention. Okay, for beam. Okay, beam has 2 degree of freedom as well. But the degree of freedom in beam, we only count in Y direction, and in Z direction. Because there is no horizontal force. There is no horizontal reaction. There is no horizontal displacement in beam. Okay, in beam. Okay, the horizontal displacement in beam can be neglected because it is always equal to 0. Okay, forces in horizontal direction in beam, okay, is always equal to 0. That is why we do not have to count X as degree of freedom in beam. So we remove X component in beam. So we only have 2 degree of freedom. For beam. Okay, it is in Y component and Z component. 2 degree of freedom in beam. And in frame, Okay, we have to consider in total all component. We have to consider all component in frame. We have to consider all component in frame because in frame there is horizontal force. There is horizontal force, horizontal reaction. We can also have vertical and vertical displacement, vertical force in frame. We can have rotation. We can have rotation. We can have a moment in frame because under beam, under frame, we can apply fixed support, and fixed has moment. Okay, so that is why under frame we have to count degree of freedom equal to 3 in X direction, in Y direction, in Z direction. X, Y, and Z. X, Y, and Z. So this is the degree of freedom for truss, for beam, for frame. Okay? And all this degree of freedom, we apply this degree of freedom, we apply to node. We apply to node. So what I can conclude is for this session, what I can conclude is, okay, I maybe continue this this with another video. We want with one video. Okay, continuing this. Okay, continuing this and continue example in trust. Okay, so that in the next face-to-face session, you will continue beam. Okay, with Dr. Tevin. Okay. Okay, what I can conclude is about this degree of freedom in trust. In trust, there are 2 degrees of freedom per node in X and in Y direction. Okay, I forgot to put node here. So all this we apply to nodes. Node. Okay, so in trust, there are 2 degrees of freedom per node in X and in Y direction. In beam, there are 2 degrees of freedom per node in Y and in Z component. Component could maybe the best word, component. Okay, component. And for frame, there are 3 degrees of freedom per node in X, in Y, and in Z component. Okay, in Z component. So before we close this session, I move back to the truss. Okay, I move back to the truss. Okay, to this. Okay. Okay, under number 5. Under number 5, okay, make sure you have understand all these 5 things. Okay, and the most important things that you need to understand is about degree of freedom, where we need to label according to unconstrained and constrained system. And if we analyze this truss, okay, conventional truss, ABC, doesn't matter. What I want to show is there are 3 times 2. There are 3 times 2. So in total, this truss has 6 degrees of freedom. This truss has 6 degrees of freedom because at A, okay, we apply 2 degrees of freedom. At B, we apply 2 degrees of freedom. We must follow this direction. We cannot change the direction. Okay, please apply this direction. Okay, and this 2, okay, is the degree of freedom at C. So in total, there are 6 degrees of freedom. There are 6 degrees of freedom, okay, in this truss because each node has 2 degrees of freedom. So if there are 3 nodes, it is 3 times 2 equal to 6. So this 6 represent the size of K. The size of K, structure stiffness matrix that we are going to produce, the size of the matrix will be 6 by 6. Okay, and we label the matrix, the structure stiffness matrix from 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, relate with the number of degree of freedom, relate with nodes in the structure, and this 6 actually we have to divide into two system, okay, unconstrained system and constrained system, depending on the support. Okay, depending on the support. So sikit lagi. Okay, looking back to this. If we analyze this trust by looking at the support, how many support? We have 2 pin support. 2 pin support represent 4 unknown reaction. 2 pin support represent 4 unknown reaction. Okay, 2 pin support represent 4 unknown reaction. Okay, constraint, unconstrained, and constrained. 2 pin support represent 4 unknown reaction, and to get total 6, okay, remaining is 2. We need total. Okay, total degree of freedom. Okay, looking at the structure, look at the support, identify how many unknown reaction based on the support. So based on this truss, there are 2 pin. 2 pin means we have 4 unknown reaction, and 4 unknown reaction equal to 4 degree of freedom in constraint system. 4 degree of freedom in constraint system. So from 4, since we know that there are 6 degree of freedom because of total 3 nodes. So we know that the remaining will be 2. And 2 representing 2 degree of freedom. 2 degree of freedom in unconstrained system. Okay, 2 degree of freedom in unconstrained system. In unconstrained system, displacement is unknown. There will be unknown displacement. We label as D1, and D2. And in constrained system, there are unknown reaction. Unknown Q, this is unknown Q. Okay, unknown Q we label as Q3, Q4, Q5, and Q6. Okay, in total, when we combine, because we have 6 degree of freedom, 6 degree of freedom, this 6 degree of freedom combining 2 unknown displacement located in unconstrained system and 4 unknown reaction located in constrained system. So the unknown displacement that we will determine first are D1 and D2, and from D1 and D2, after we have determined this, we substitute into force displacement equation, and then we can continue to calculate Q1, Q3, Q4, Q5, Q6 represent reaction at the support. Okay, so this session is all about the concept. So please try to understand about the concept of stiffness method. Okay, I will produce one video. Okay, to continue this. Especially for trust, I will tell Dr. Teven, I will cover trust for you. Okay, I will cover trust for you. Maybe replacing the previous week number 9. Okay, represent the week number 9. So I will continue this for another video. So make sure you watch the video in order to understand about all this. Because whenever we start doing example, you will understand more about what is analysis of trust using stiffness method. Okay, so that is all about today's session. Okay, today's section, week number 10. Actually, this one should be present in week 9 last week. Okay, so I will continue with another video to cover these 2 weeks. Okay, hopefully you will understand, and please watch to understand. And in the next video, I will give you task for you to do exercise to see whether you understand or not about the stiffness matrix for the trust. Okay, so thank you very much. Thank you for joining this session. Okay, you can also repeat this session. This is live event Microsoft Teams. You can use the link, okay, to watch again this session. And this session I will download and upload into the YouTube as well. I give you the link after this. Okay, thank you very much. Thank you for joining this session. Assalamualaikum warahmatullahi wabarakatuh.